Hi, welcome to Useful Tips and Tricks in Physics. Try and say that fast. Now, what we're going to do is we're just going to muck around with some things and I hope that will help you understand a few things. So we're going to be talking Van de Graaffs and a few other bits and pieces that might lie around the lab that people might go, what the hell is this? And this might give you an idea of some things you can do. So this is just sort of going that way. Number one, gotta love the Van de Graaff generator, especially in winter when it's crackling fine, and it should be doing it today. First thing about Van de Graaff generators, they need a little bit of maintenance. So what I tend to do is before you're going to start using them, first of all, clean it. So, number one, all of this stuff here, if it's clean, will help a lot. Won't guarantee you're going to get it, but certainly in dry weather and winter is good. The outside of this, just using hot, warm soapy water, just give it a wash down and dry it with a tea-towel sort of routine. All of this comes apart as well. Now, I'll do this very quickly and show you how simple it is. Don't be afraid to pull this apart. Don't have it plugged in. It's not plugged in, no, before you start. Alright, bottom comes off. Come back to that later. Basically the top part here comes apart. I'll do this quickly so just in case you've seen this stuff. Pull him out. Separate these parts. The roller will come out like so. The roller can then be taken off and you can change your belt, etc. I will normally take this all down and wash out the entire thing, including the nylon roller at the bottom. Wash the whole thing, give it a good clean. Every now and then a new belt helps. They do get, I don't know what it is, oil in the air, I'm not quite sure what it attracts, but certainly after a while they don't work so well. Putting it back together, same thing, put the band on first. And the reason I didn't let go of the band is because otherwise I've got to put my hand down this very thin pipe and my hand only just makes it. Anyway, so assuming it's cleaned out, I haven't tested it today, see if it's working, and we'll soon find out. When I first put it back together, I like to turn it on, now, like so. Before you put the top on, turn it on like so, it's on full, and I can hear a little crackling noise coming from the top here. So it's not going to get much charge, it's actually, you won't get zapped, but I can hear discharging happening to the air at the top here. That tells me it's working well. All I need to now is not have sharp edges, which is what this is about, to build up higher voltage. When you have sharp edges, it will discharge into the air because it builds up electric fields much higher, and the air itself will ionise. So, top on, good idea to have the wand plugged in to stop any stray sparks. Don't mind the stray spark myself, but if you don't know they're there, that can hurt. Okay, power on, see what it does. Hopefully this doesn't destroy my computer. Okay, that seems to be fairly strong. So, turn him back off. Discharge him out. Okay, some things. Well, we've all seen this one. This needs a bit of a comb, but you'll be able to do sort of routine. This is where you get, as the charge builds up, it doesn't like being near it, so it will spread out. Give that a bit of a comb would be good, but that's working fine. This won't charge up as much because we're now actually ionising into the air. You can actually see it, and I can hear it buzzing and carrying on. Fine. Turn that one off, get rid of that. Okay, lots of other little demos. If you're insulated, you can hang onto the top and your hair goes up and all that sort of stuff, which is always good fun. The biggest problem, of course, is the discharging. I tend to use the plastic chairs, and that way if the child gets down off the chair with the jumping, there will be a spark, but because they're jumping on their feet, they won't feel it, and it's all fine. Please check for things like hearing aids, pacemakers, epilepsy, etc. If in doubt, no. That's essentially the way it goes. Alright, one of the ones I like is pop down to your local bakery, pick up some pie things, or eat a lot of pies. Custard ones are nice. And this is always fun. Kids seem to like this one because I like to try and catch them and they can't. But it's always fun anyway. Building up same charge repels, the repel turns into pick them up as fast as you can. Fun, isn't it? Anyway, so basic things. Kids seem to like that one a lot. Now I'm going to let this keep going with the wand down further. You can hear some clicking going on at the moment. Here you're actually getting large zones of ionised air around the bottom. If this is in absolute pitch black, it looks fantastic. You're actually getting purple flames about this long coming off it, which look fantastic. But don't do that probably with lots of kids. But as far as teachers and things like that going, yeah, dark spot looks great. I've tried to photograph it and not having much success with that one. Anyway, that's essentially that with the Van de Graaff. Okay, alright, so next one that people tend to have a bit of trouble with is the old Hodson Light Box. The light boxes have got a lot of uses, but if you don't use it properly, it can be really annoying, let's say. And it's always good to let the students have a play with the damn thing, but you've got to use the right side. So, number one, AC and DC doesn't matter. The old, good old illegal incandescent lights in this one, so it doesn't really matter. Alright, this one has got two sides. G'day. Two sides that are open. The side that's closest to the bulb has also got some flappy wing mirrors. Don't use that side. Okay, you can use it later as, you know, there's other things you can do like combining light and stuff, which I'll have a bit of a muck around with in a minute. Realistically, you want to use the other side because there's a lens in there. So the first thing is to watch paths of rays and things like that is the first thing I want to do, and these slides come with it. So they're sort of like little combs. Now, these little combs here are really good because if you pop them in, what I tend to use is one in one side and the other one in the other side, and then you end up with a nice dark room again. So this way you're controlling the light. Now, I'll hold this up as I muck around with this as we get started. The first thing you want to do is get nice parallel beams. So a bit of power, get us some light out of there. I'll just go a little bit stronger, up to 8. Okay. So you can see there I've got the beams coming out. Now they're fairly parallel at the moment. They're not too bad. But by moving that mirror, that little lens, they're definitely not parallel at the moment. So the idea is to muck around with that lens to get nice parallel beams out of there. The more beams you get, the better it looks. Alright. Like so. You can adjust it so you can have them coming in or out. It's up to you. So once you get them parallel, then you can start to muck around with how lenses and mirrors work. So this is looking at like optical systems, telescopes and stuff like that. Okay, so a couple of things you can do with this one. Once you get it set up, having it on the table, mucking around with some of the little lenses. There are prisms and things. I tend to come back to them a bit later. The first ones I tend to do is, I mean, this is where assuming we've gone past some of the other activities. If I come back to a single slit, we can look at a single ray, a bit like a laser, and we can investigate the path through blocks, investigate Snell's law, and how light gets refracted through prisms. You can do it as well if you use, for example, a laser, but you're not going to be handing lasers out to every single kid, okay? It's a little bit trickier. So probably try it this way. It's sort of like these things are nice and safe because they're low energy and all the rest of it. The kids aren't going to be staring down the end of a loaded laser and certainly putting it into other people's eyes, which is you don't want to do. So a single slit at the end here will give you the ability to look at Snell's law. There's plenty of good pracs on that. If you look up online, you'll find plenty. I like the other version where you have 4 slits coming through and you can look at your lenses, how the lens works. First of all, if they've done Snell's law, you can go to the lenses. If they haven't, go your mirrors. Put your mirror down and you should be able to show that it's got a focal point on the mirror. A focal point giving you the same sort of idea as a telescope. So with a curved mirror at the end there, the focal point's the important part. Investigate the difference of the focal points on both sides of the mirror. You do get a focal point, you don't get a focal point from the other side, and also the shape of the mirror, whereabouts the focal point is. Some things along those lines. You can do little pracs on those ones. Which gives a better image, which gives a better focal point. These ones do. The more curved they are, the more problems you tend to have. So short focal length telescopes aren't so great. The longer they are, the better, which requires a flatter mirror. Lenses, same thing, you get a focal point. We have a second lens, much more curved, but the focal point is nowhere near as good. So again, same concept. With telescopes, longer focal length, and microscopes for that matter, the longer the focal length is, the better the image tends to be. So you can do some experiments with those. Now, they're the standard ones that most people will probably know, so I'm not going to go too much into those. Some of the more fun things you can do. Okay, you might have seen the LED lights that give you the 3 colours. So you can use these, shine them on a single target, and you can get white light coming out of them. Got little magnets, you can put them on the whiteboard. Same thing, it actually gives you a beam of light, and where the beam crosses, you hopefully get white light. You do tend to find the reds fairly strong, but if you can find the right crossing point in the middle there, you might get a slightly white. The lights in the room are just blotting it out a little bit. There's sort of white in the middle there where they cross over. But you can sort of see in the middle here you've got a convergence, and it's more of a purple colour at the moment. So you muck around with where these sort of fall, and you can actually get more closely to white. You can do the same with the Hodson Light Box. Take that one out, and I've got here some slides that come with the Hodson Light Box. So I've got green, cyan I'm going to keep out. So I'm going to go for my red, blue, and green. We don't have red. Magenta will have to do. So this is where the wings come in. Your slide can drop in on the side and in the front. I've now got one torch, or one light source, has now turned into 3 beams. With the filters on there, turn him on again. And now we can actually aim our mirrors this way so you can see it. Turn up a little more light. And so now, by aiming the mirrors on the side, it has to be reasonably dark, but you can see I've got a whitish colour in the middle there. Now I've got blue, red, green, and in the middle, well, close to white. So that one works quite well. And so this way you can actually muck around and move things out and about, and you can actually see your 3 colours doing the job as you need to. So that works quite well. Okay, first thing, you've got to get a set of these ones. Used to sell them in Woolies in the party area, but they're a bit harder to find these days. Fireworks glasses, rainbow glasses, a whole lot of things. Diffraction gratings in each lens, or in each eyepiece, and they work extraordinarily well. I usually hand these out to the kids, and I'm trying to find a decent supplier that the kids can go buy them, because they all love them. You do have to tell them though, when they go home and do this with the downlights, their child is not on drugs. They are high on science, because they'll walk around going, oh, check it out, man. Now, if you haven't seen these, we'll try this. Does that work? Good. Rainbows everywhere. Now, the great thing to do with the rainbows, there's a few things you can do. Number 1, you look great. Number 2, you can muck around with some of these lights. Now, if we start with the incandescent light that's in the light box, for example, and I use this end, by looking at this one, actually, what we might do, it's popping on.
More of a star, but yeah.
Okay, a star. But pick one of the directions, because you've got your 4 north, south, east, west, as well as your diagonals. You've actually got a bunch of rainbows. Concentrate on one, and if you concentrate on one, you'll see that you get your full rainbow coming out of an incandescent light. Now that's fine. Actually, I want to try the other side and see if this works better. Does that work better?
Too overexposed.
Thought so. Go back this way. Okay, so your incandescent light will give you the full spectrum of your rainbow. So look at some other ones. So for example, I shine this one at the, now, is that okay? Okay, now can you see the red? This is a red LED. If you notice very carefully, look really intently at it, you'll see it's not purely red. You actually have got a little bit of green in there and a tiny bit, maybe even a bit of blue. It's hard to quite see, but it just can be picked up if it's on your face. It tends to work a bit better. Moving up to blue, this is the top end. So, looking at the top end, can you see any red in that one? No. Okay, when you put them on your face, you can actually see red on the side. Green, now I don't know if this is going to work. Nothing in that one, so we won't worry about that one. But if you put them on your face, you will actually see some other colours that are actually in there. LEDs are not lasers. I'll show you the laser one in a second. You don't show them in your face, so I won't go there. So they're fun. So just to get the idea of colours and lights and stuff. That, of course, can be put across once you start looking at fluorescent lamps or discharge tubes. You'll get your whole spectrum coming out. You're starting spectroscopy. You're talking about all that sort of stuff that can keep on going. Of course, with astronomy that I do a lot of, then spectroscopy is fairly important, and you can start to talk about the idea of elements being seen, and the fact that we've known about the elements in the stars, for example, before Ned Kelly was running around Australia. That's fairly impressive, and I like talking to the kids. We knew what the sun was made of 100 years ago. We didn't know how it worked, but we knew what it was made of. How do we know what it was made of? Well, we hadn't been there. When I was a kid, I could never work that out, but now it makes perfect sense. So I like to tell the kids those little stories to bring things into perspective. All right, now lasers. Now I'm going to get one of these glasses again, and this time what we'll do is I'll shine the laser through them without the eye on the other side. That's better for you. Okay, I might start off with, I'll go for red, green will show up a lot. Okay, now what we're going to do is, we're going to aim at the wall. Okay, so there's the pattern you get from this. Now this is a diffraction grating that goes left and right and up and down. So when you're holding the laser on the end of the diffraction grating, and I'm just having trouble holding all my things with two hands. Okay, this is trickier than I expected. There we go. Okay, there's your central one. The grating goes up and down and left to right. So off to the side, you get another bunch. So off to the side, 1, 2, 3, they're the horizontal ones, and then you've got the ones going up and down. But because you're going up and down, the sideways will also help by making more. So you end up with a fairly large pattern. So that's what the effect you're getting out of these things. Now, things you can do with lasers in this, get different wavelengths of laser, and you'll find that there's a different distance between these. So that's just one of your physics ones that you can muck around with. The fact that this light is not just splitting it up into colours, but you've actually got maximum and minimum interference patterns. So maximum in the middle, there's another maximum, there's another one. They are all equal spaced, and using those distances you can find out the wavelength of your laser and see if it matches your laser itself. Alright, well, a couple little things on light there that are fun. Once you get a bit further into the astronomy area, which I sort of quite like, a lot of people are scared with astronomy. It's not hard, it's great stuff. But yes, there is a bit of a learning curve that some people freak out by. First of all, with telescopes, if you get a cheap telescope to start with, people are less worried about it. So it's not a bad way to start getting into things. These ones are quite good. This is the Galileo scope that you used to be able to get at the moment. Apparently they are still available in Australia. They're still making them. They made these ones to not pretend that it was really good, but say, look, this is a telescope that you can put together, but the advantage is you can also pull it apart. Well, in fact, when you get it, you have to put it together, in fact, all the way. So you can actually disassemble the entire thing, and it's safe to do so. Except I can't get the last part to separate, of course, as usual. There we are. And you can show them what's inside the telescope. Nothing much, really. So, what we got inside here, we've got the outside tube, you've got the lens at the front, and you've got the draw tube at the back, which is hollow, which you put your eyepiece into. So, how on earth is that a telescope? Well, that's actually pretty good. Lenses. Hand out a set of magnifying glasses. That's the first question you get. Can we go burn some ants? No, you can't burn ants. That's wrong. But what you can do is you can make images. So first thing, I let the kids muck around with the magnifying glass. Oh yeah, look at my fingerprints and all that sort of routine. The next thing is to show them what they're really used for. The majority of lenses are not used to magnify things. They're used to project images. So the next thing I get the kids to do is, well, see the light up there, can you get the light onto a piece of paper? And when you do that sort of stuff, you get an image. And that is a focused image. Do it to the outside. We've got the window shut at the moment, but if you do it to the outside windows, you get the colours as well. And the kids freak out. Oh, look, there's everything outside the window. And you walk along and, oh, it's upside down. They freak out. They love it. It's one of the best things to see them do. You can see on the internet at the moment, there's little plans actually where you get your mobile phone, turn it up nice and bright, decent lens in front of it, dark room, and you get a projector onto a wall. Got to be fairly bright phone, but it does work. Better lens, better quality image that you get. Does the lens have to be as big as a phone? No, it doesn't. So it still works quite fine. Then how on earth did we invent the telescope? Well, it goes back to patents and legal things, if you ask me. Hans Lippershey apparently in Denmark said he invented it. I doubt it very much. I think it came down to a couple of kids coming into a spectacle shop and picking up a few lenses. Now, if you pick up random lenses and do this sort of routine, you don't sort of get too much. It's hard to, you sort of, no matter which way you do it, you can sort of see, oh look, a single thing, double thing. In fact, when you hand these out, the kids all go, oh yeah, check this out, and all that sort of stuff. Now, you can muck around with things, but these ones are good. If you've got the little tiny magnifying glass at the bottom, the shorter focal length, you can do a telescope. You want a short focal length and a long focal length. Hold the short one up to your eye, hold the long one out at arm's length, and look through until you can get a decent image. So you'll end up with a blurry picture with a circle of clearness in the middle. And you can bring it into focus. You've got yourself a telescope. That's all a telescope is. The only difference is we put the two lenses, sorry about that, in a tube. Move this in and out to get your focal length. That's all you do. And that's the rudiments of a telescope. So, with the Galileo scope, it's actually fairly decent. They've spent the money on the lenses, not the outside of the thing. So you do actually get fairly decent. Once you put it together, now like that, and where'd the other bit go? There it is. And I think I'll put it back together wrong. Just squeeze this over the top. Yep. Okay. There's your telescope, eyepiece in the end, and you're away. All you need now? Well, it'll work. You can hold it up, but it's a bit awkward. Tripod. Tiny little tripod, just a camera tripod, does the job. And this is now usable outside, like so. Aiming, there's no finder scope. You've got normal sort of gun sight focus, finder scopes. They spent the money on the one lens here and the one lens at the back here. That's all they've done. You can set it up a different way, so you can change the eyepieces from a normal telescope into the sort of view that Galileo had. That's why it's called the Galileo scope. So if I can take this end out, and it's not being very cooperative with me at the moment. Yeah. Put that lens in, and that is the view that Galileo had. And when you look through it, it's quite stunning. I don't know how he found anything. Without television, I guess it helps. So with this eyepiece in here, it does work. You get a magnified view, but it is incredibly small. It's very good to show the kids. The other thing about this lens is there's another piece that puts it together, and you can put it on. This attaches to the back of that one, and you end up with what's called a Barlow, a 2x Barlow, which doubles the magnification of your standard lens. What can you see through this one? Craters on the moon, really well, really easily. After that, the planets, Jupiter. You won't see too much detail on Jupiter, but you will see the moons of Jupiter, no problems at all. Will you see the rings of Saturn with this? Yes, you will, quite happily. The rings of Saturn will turn up quite well. Rings of Saturn can be seen through this. This is more powerful than a pair of binoculars. All your major things you can see, clusters, globular clusters, open clusters, look fantastic. It does get tricky when you're looking for nebulas and things like that. It's not really designed to quite go that deep, and certainly galaxies, this one's not in the reach for galaxies. But as a simple little scope, it's fantastic. It's one I recommend. For every school should have at least one of them. And that was the purpose of when they built them in 2009, the International Year of Astronomy. They were designed that every school would have one. Actually, every school would have a dozen. And in class, kids would put them together and then use them. So that was the idea of them. The prices are a little bit higher than what they were supposed to be $20 US dollars. They've gone up a little bit, I understand, but they're well worth it. If you haven't got a scope at your school, get a couple of these at least. It'll do the job, and if you want to go further, you can go further with the scopes. Alright, one of the things I like doing with these, and you can actually do it with a pair of binoculars, which I won't worry about at the moment, because they're behind the camera person, but doesn't matter. Yep, and magic! Okay, pair of binoculars. These are very cheap binoculars I bought years and years ago. One of the ends broke off. Doesn't matter because I just used one anyway. Don't look at the sun, but you can shine the sun through them quite happily. So, just like I made the image on the piece of cardboard, the sun up here, attach this to a tripod with a retort stand, and then focus the focuser, and you'll get an image on a piece of card behind the pair of binoculars. This one works extremely well. Same thing. Did this with my class the other day. We had a fantastic view of 3 huge sunspots right in the middle of the sun. It looked fantastic. So again, lining it up to the sun. Never look through the bottom of it. They do have the warnings on there. Don't look at the sun, but you can shine the sun through it. So by shining the sun through the middle of it, holding a piece of paper at the back, you'll get a lovely image of the sun. The further back you go, the bigger it gets, but it also gets fainter and harder to see. So you've got to sort of trade off detail and size is what it tends to come down to. If you can build a shade that will fit over the front of this, a piece of cardboard that will just slot onto the front, act as a large shade, you get much better detail. When we were doing it the other day, we were getting the sun about 10 to 15 centimetres across, and you could easily see 3 very large sunspots right across the middle there. Great view, no one gets damaged, you don't look at the sun that way at all. Something that can be done, our kids seem to like this, it's not much use unless there's something more spectacular happening. Some solar glasses as well. These are designed for solar eclipses. You can look at the sun through these. I was working on a committee that managed to get the safety of these approved in Australia. Up until then they weren't even legal in Australia, which I found a bit hard to believe. These have got the European safety standard on them, and if it's got that, it's legal in Australia now. That took us a long time through bureaucracy. The kids put them on, the first thing they say is, I can't see anything. Of course you can't see anything. You need the sun before you can do that. When you look at the sun, you'll see a very small circle. Unless you've got Venus going across it or the moon going across it, not much else to see, but the kids seem to enjoy doing that. That can go along quite well if you're doing some solar stuff in the Sun, Moon, Earth section of Year 7 and junior grades as well. Being able to safely look at the sun, for some reason the kids, well no, I understand it, the kids really do enjoy it. They have a great time with that. So I thoroughly recommend you get a set of them. Again, a bit like the rainbow glasses, don't get the two mixed up. The solar ones are quite cheap. You're looking at $2 a set sort of routine. Buy a class set. You will have to replace some because they are very, very popular with some people at home. Thoroughly worthwhile getting them. We do have some solar eclipses coming up in Australia in a while, not just yet. I think it's a few more years off, but I think you'll find that there will be solar eclipse fever in Australia in about the next 8 or so years. Okay, so the telescope, like I said, nighttime you can see things, daytime you can see things, it's really quite good. A couple of things that we've also made up that might help the understanding of astronomy. A few things you might want to play with. Sun, obviously, moon, phases of the moon. Now, I've seen this done a few times where they basically get a ball and you say, see the ball, see on one side you've got the sun, see on the other side you don't have the sun. Light, shade, light, shade. Can you see the phases of the moon? It's really hard to see phases of the moon with these sorts of things. I don't care, unless you've actually got a spotlight in the room, it's really difficult for the kids to see the shaded part because you can see the reflections around the room. The shaded side is still lit up. It's really hard to get that concept across. So, paint it. Nice and simple. Light side, dark side. Now, you've got to explain though, you've got to be able to explain the fact that the moon is actually rotating at the same time. But we're just talking about the light side and the dark side are not rotating in this situation. One side faces the sun all the time, the other side doesn't, and in between. This way, you can see the phases so much easier. As long as you get across the idea that the moon is actually rotating inside this sort of shape. This is just the light dark. So, the sun's over here. Bang, no worries. And here we are at quarter moon or half moon, whichever way you want to talk about it. And you can see the phase. The kids can draw it really easily. Move the moon around, or actually I tend to move around this classroom, and you can show them that we can get to crescent moon, gibbous moon, full moon, back to gibbous, quarter or half, crescent, and new. And don't move the moon around. Keep one spot consistently the sun. So normally what I do is I'll make the back of the room the sun. And that way I hold it this way and say, okay, can everyone see the moon? Yes, you've got a full moon. Yes, well done, you've got a full moon. I will then move around the class until I'm an eighth of the way around. Okay, what moon have we got here? Well, it's not quite full anymore, but it's not crescent. What do we call this? Well, it looks like a pebble sort of thing. Looks like a, sort of this rock. Now, that's where the name gibbous comes from. Rocks that are weird shapes are gibbous rocks. I understand. So, you've got your gibbous moon, move around to your quarter and move, and so I move around the room. They sketch it as you move around. It works really well. The kids understand phases so much easier by doing it that way. At the same time, you can always pull up a moon and then talk about, another ball that's not shaded, and you can then talk about what the kids see from the Earth and all that sort of stuff. Okay, right, good. Schools have got these things, use them. So here's my planet that I'm going to use. I can muck around with a ball here, which I've got to act as the sun. I didn't know that was on loan from the dance department. Okay, here's my sun. Put it somewhere, but this doesn't really work because the sun's supposed to be an immense distance away. So I just sort of put it at the back of the room, saying it's not at the back of the room, it's much further behind that. Forget that. Moon. Back to my moonage. We'll come back and use this, but this one we now have to not pay attention to the light dark. We'll come back to that. So, first of all, which way does the Earth rotate for the kids? Well, it's hard to sort of say. Because we're in Queensland, we've got a bit of an advantage. Well, no. It should work out the same for everyone. First thing, Australia. Here we are in Australia. We're on the eastern side of Australia, so I sort of say to them, look, pretend you are the globe. You've got Australia attached, and I've done it before, we've actually cut out Australia and stuck it to their tummy. Where are we? And you point onto the eastern side, which is on my left, okay, here. Now, where does the sun come up? Well, it comes up to the east, so which way would you look if you were doing that? Oh, you'd look that way. So if we're here, we're looking that way to see the sun come up. So we know the sun is going to be over there. Now, which way does the Earth rotate as this goes on? Now, first things, it's no matter what they say, they keep on saying that the sun is the centre of the solar system. It doesn't work in our heads. It's actually better to think about the Earth not moving, like pre-Galileo and Copernicus, and think about the sky moving. So, let's be stationary. We're here, or here. Now, which way does the sun go? It goes over the top. It rises from the east and goes over the top. The star moves, the sky moves. Okay, now we know that's not the situation. So once we work out the sun goes from the left to the right, okay, let's stick the sun so it's now stationary, and which way do we need to turn to get that to happen? And all of a sudden you can see quite simply, oh yeah, sun's over there, it's got to go across the top of my tummy. Oh yeah, I turn this way, towards the left. There's the rotation of the Earth. If you're standing east at Byron Bay, leaning out like so, you're doing the whole, Titanic sort of thing off the bow of the boat, okay? That's the direction we're going. Wings in our hair, we're sailing towards the east. That's the way the planet goes, simple as that. So, how do we get that idea? Go to the top, which way is it going? It's going anti-clockwise when you look from the North Pole. So, Earth is going anti-clockwise from the North Pole. No problem. We've got that one worked out. How does the moon then work? Well, the moon, as the Earth goes around, the moon seems to be moving across the sky. So let's go back to moving across the sky. The moon is going across the sky in the same direction as the sun. Oh, okay, so in other words, the moon's not really moving that much. The Earth is rotating and the moon's staying stationary, sort of, but the moon does move. Every night you go out, you can see the moon. If you can see the moon, or during the day you can see the moon. The same time the next day, where is it? It's actually one full handspan further towards the east in 24 hours. So it actually is slowly moving in the same direction as the sun. It chases the sun. Now, if it's chasing the sun, then it must be moving in the same anti-clockwise. Because if the sun's not moving, it's basically getting closer and closer and closer to the sun. The Earth's doing this fantastic spinning, and the moon is doing this. The moon is going in the same direction as the spin of the Earth, just a lot slower. Instead of being 24 hours a spin, it's 27.5 days to do a spin. Call it 28 days. Handy thing being 28 days, because you can talk about the quarter phases, new moon, quarter, full, quarter, once a week. So if a new moon is on the Monday, new moon on Monday, quarter moon is on the following Monday, full moon's on the following Monday, and it keeps on going. It does move slightly, but that works really quite well. Each week you've got an extra phase. And in that time, it's moving around in the anti-clockwise. So Earth spinning anti-clockwise, moon spinning anti-clockwise in the same sort of direction. So, which way does the planet go around the star, around our sun, which its name is Sol, by the way? So, we saw I was with a friend and we saw it at a conference, and they were talking about this in America. And what they would do is they put up the star signs, okay, the zodiac all around the room, and they tell the kids to go to the place where the zodiac where they were born in, sort of routine. And they said, oh yeah, that's fine. And then they said, all right, go to the next star sign. And I looked at my mate, I didn't have a clue. I do astronomy, I don't even have a clue what they are. All the kids knew what the next star sign was, and the one after and the one up. They even knew the dates. I haven't found a class that knows it yet. I don't know if that's saying something about us or America. Anyway, so with the astronomy signs, it's hard to sort of fathom, but ultimately everything goes around the sun and everything's going in the same direction. So the Earth's going anti-clockwise from the top, the moon's going around that anti-clockwise, that's all going around the sun anti-clockwise, the sun spins anti-clockwise, everything seems to be going anti-clockwise. Except for Venus, which is tidally locked to the moon, to the sun, and also the funny one, which is Uranus, which is on its side. That's another one to laugh about. Anyway, what else can I say about the Earth, Moon and Sun? I haven't even got to seasons. Do you want to do that? Okay, seasons. Cranking. Again, Earth was once spinning around like this. No tilt. Along came, we think, a large object and gave it a push over on its side. That large object could well have been Theia, which created our moon. Earth's going around the sun, and in the same orbit we think there was another planet, actually about this size, and it was following the Earth, not coming in from great distance, smashing into it like a meteorite. That would have been obliteration for both planets, and nothing would have come after that. But we think they were both going around in the same sort of orbit. Because there's gravity between them, they just got closer and closer and merged. Now, this is about 4 billion years ago. When this happened, these two planets were pretty well liquid, and it wasn't an explosion, it was more of a gloop, if you can imagine. But in that gloop process, a lot of stuff shot off into space. These two planets then merged into one planet. There was no water at the time. It would have been a pretty inhospitable place. If there was life, it would have been restarted instantly. They smashed together. The stuff that formed around the outside forms our moon eventually. We had a ring system at one point, which would have been so cool to see. We got the moon out of it instead, so that's fine. Now, come back to our planet. We think that might have been the impact that may have pushed it on its side. Thank goodness it did. It gave us our moon, which has stabilised our orbit, gave our tides, keeps our water churning around, keeps our oceans where the life began, all fluid and mixing, which is great. The spin of the Earth has now got a tilt. Now, getting across the seasons, a lot of people just sort of say, oh, you can see, like when it's like this, that if you're the sun over there, you can see Australia's copping the full light, and in winter time, it's it's around the other side of the sun, and we're down under here. Yeah, that sort of works, and you can sort of do that as an exercise, but what I like playing with is actually torches. As long as it's got a decent beam on it, you can see how much light is falling from a distance. So you can see a circular beam there. That can be our sunlight. Now if I put it on facing directly on the front here on the equator, you can see it's a nice sharp round circle. But what if you go north and south? You can see now it's elongated. You can actually put this onto a piece of paper, like so. That's summer. Now, providing you keep your torch at the same distance, this will work fine. So if I keep it there, then tilt it down sideways, you can now see you end up with a bigger circle. The bigger circle, you can actually get the area by just counting up on a piece of grid or something like that, and you can actually find that the same amount of light now falls on about 160% of what the original circle was. If you got the same amount of light on a larger surface area, therefore you must have less energy per meter. Less energy per meter, you can work out the percentages of that would be appropriate. It will go to the same temperature drop. That's the first reason. The second one, you've got another reason. Once you're down south, how much sunlight do we get in summer? Not 12 hours each day. That happens around the equinox. At summertime, we're getting about 14 hours of sunshine per day. Wintertime, you're getting about 10 hours sunshine per day where we are. So you've lost from summer to winter, you've gone from 14 down to 8. That's almost half, instantly there, half the amount of energy in that respect. Then you use this process and you're down to about another 70% of that energy. So when you work out how much energy actually is falling on a single spot, you can do that, and this is a great little thing with percentages you can do. You incorporate mathematics into this sort of stuff. You can actually work out, you end up with I think it works out to be a bit less than half the energy falling per square metre, winter, summer. Hence, cold's hot. I like doing muck-arounds with this sort of stuff, like, what are the kids' preconceptions with what causes winter and summer? And the classic one is winter and summer caused because we're closer or further from the sun. And a lot of kids actually think that is the answer. We've got to be closer to the sun, therefore it's hotter. It turns out they're right, but not in the same way. We are closer to the sun by about 1 or 2%. Not enough to make a massive difference. 1 or 2% is nothing compared to 60 to 100, 60% up to 100%. So the biggest thing is actually the tilt, of course, that gives us our seasons and makes all the difference, giving us lovely climate and warm, hot summers and all that sort of stuff. Another one you can also do, this is one that's got a little bit scrunched, I meant to show you earlier. You can set these up. So we've got split pins, sun, moon, and earth around the place, and the idea is these ones you can get the whole thing to rotate around the sun, and while that's happening the moon can rotate around the earth at the same time. Now you'll notice we're looking from the north pole of the planet, north pole, so the whole thing anti-clockwise. So that one the kids do enjoy, but they can keep those ones because it gets a little bit tricky. You can also muck around the scale on these ones, not the sun, but where should the moon sit compared to the earth at this scale. At this scale here, you'd be talking probably about 8 metres away. That the kids get a bit surprised by that one. It's not quite so close. Other things, astronomy-wise, I guess as far as sun, moon, earth, tides. I won't go into this one, but you can talk about the idea of tides. Gravity between the moon and the earth sucks the water in. The bulge on the front, that's easy to explain. That's one's a fine one. How do you explain the high tide on the back though? Moon's over there. How come you get a high tide on the back? This is one which you've got to be a little bit careful. Pick the smallest kid in the class. Come out here, sunshine, grab hands and go around each other, forming a small moon, large earth sort of situation. Don't go too fast. People get upset when they fly through windows. But spinning them around a little bit and try and get them to see. Is the teacher staying still while you're going around in this sort of dance? And you'll see the teacher's actually got a slight wobble. So it's not like the Earth's still and the moon goes around. They actually go around each other a little bit. So there's a slight wobble to it. Now that slight wobble means that the back is moving faster because it's out here. So the centre, instead of being through the middle of the Earth, is actually through about here, and the Earth goes around that point. It does this funny dance. That gives you your centripetal or centrifugal force, let's call it, out the back, that gives you your high tide at the back, which is lower than your high tide on the front. There's your two tides. When it lines up with the sun, you get a higher tide yet again, and that happens at new moon. And you've also got your king tides that can sometimes occur in January and December, when you've got the moon, the sun, and theoretically the galaxy. The centre of the galaxy is lined up as well. I don't know if that's true or not. I've never looked at that. But you're certainly lining things up. Wouldn't that be the end of the world? Wasn't that movie? The 21st of December. It happens every year. The sun, the galaxy, and you can get the moon lining up all at once. Hasn't finished yet, so it seems to be going okay. Right, well, these are just some of the things that we're playing with at the moment in the school. Physics stuff can get quite complicated. Don't be afraid of it, but all this stuff that can be found online. And it's sort of one of these things that, with teachers being afraid of it, if you've got the idea as a technician how to, spark things up, so to speak, of course the Van de Graaff is always the funniest one there. But you can bring these things to life a little bit more. Don't be afraid of them. These are literally toys. They're fantastic to play with, and there are plenty of good toys out there. A lot of the desktop toys are good fun to have in a classroom. And if you haven't got a dunking bird, you've got to get one of them. Anyway, I can't think of anything straight off the top of my head, so thank you very much. Like I said, this is what it's all about. It's having fun. Thank you.